Okay. So as I said, this session will be devoted to exploratory spatio-temporal data analysis. A particular kind of exploratory analysis, in the same that it is the analysis that it is necessary or is important to know or to find out this structure that is intra-distributional. So because of course you can do a lot of spatio-temporal data analysis, but this is a a peculiar or a specific, we could say a specific type of analysis that is usual to detect this kind of intra-distributional mobility and to do this kind of analysis on convergence, divergence, and even to detect spatial regimes, because they follow different trends of different kind of intramobility analysis or evolution. So it's part of this methodological procedure I was presenting the other day. If you remember, it could be split into 6 steps. So the first one was the one devoted to the spatio-temporal analysis, exploratory analysis, and second and third was more or less the content of the next session. So analyzing the intra-distributional mobility with Markov chains and the role of spatial dependence in this intra-distributional spatio-temporal mobility. And for the last session, before your presentations, because if you remember the very last session, it will be devoted to the presentation of your the whole number of assignments as a whole, so you must sum up all the assignments and present all them. And your assignments, as you are looking, will be repeating or reproducing all these steps to your own database, panel database. So this is what you must do. And okay, so this is another way of presenting the methodological procedure. So this exploratory analysis has a double aim, as I could see. So first, analyzing this dynamic of going to a convergence, a divergence, or a convergence, but in a form of some clubs. So it's regimes or clubs, spatial clubs, and well, the other analysis is detecting this kind of urban regimes, urban or whatever. So because you can, of course, analyze it's urban because of our paper, but you could be analyzing countries. I saw one of your databases was on countries, so no problem at all. The only problem with the countries, as I said the other day, is that these countries should be more or less close to each other, or the best thing is that they could be joined, so sharing common borders, like the European countries, but not one country up and down, and because if they are split throughout the world, it's complicated, to build a reliable spatial weight matrix. So neighborhood is not very reliable. If you say that, for instance, I don't know, but some African country could be neighbor to Spain. Well, it depends, maybe Morocco, but if you go to the southern part of Africa, it's not going to be true. But perhaps in your sample, Spain is the closest country. I don't know if I explain myself correctly. So it is necessary that your country sample, the units could be more or less joined. Okay? And well, this is our first step in the methodological procedure. What kind of charts, of maps could be interesting to analyze this spatio-temporal intradistributional analysis? So to detect trends in this analysis. We propose using some statistics measures and some representations And what we want to do is studying the evolution in time of the mean value, the dispersion, and the shape. So the first, second, and third and fourth moments, you know, of spatial distributions. So which kind of analysis could be interesting? You have here a few box plots, of course. You can add some others if you wish. So in Geoda, if you know this software, you have lots of possibilities to do this kind of spatio-temporal analysis. These are, to my knowledge, the most interesting ones. This is why I propose here these ones on the slides. So first, box plots. Second, standard deviation, coefficient of variation charts. Third, scatter plots. For Moran's scatter plot, which are not the same thing. 5, Lisa maps, of course, normal maps, but the Lisa ones are specifically for something, as you will see. 6, average charts, and 7, kernel functions. Okay, so we are going to build all of them in Geoda, with the exception of the kernels that will be done in R the next day. But I'm going to introduce the kernels too. Well, what about the box plots? Because the box plots are quite common. So I suppose that every of you know what a box plot is. But just for a review, this is a way of Geoda has to show a box plot. So it is a chart which focuses on the quantiles of the distribution. So the data points are sorted. So what the software does is sorting the data points in a variable from small to large. So smaller values are down. So in this part, down, and the largest ones are up. Okay, the median. So the 50% point. So it is the value of the variable that splits the distribution into two equal parts, equal in the sense that these parts have the same amount of observations. Okay, so it's the 50% point. It is represented by the horizontal bar. So you can find here a horizontal bar with it more or less clearer. It's like a red. This is the median, and you can also depict, as it is the case here with Geoda, the mean value. The mean value is drawn as a point. Here it's a point in more or less in green. Okay, in this light green. The brown rectangle. So I don't know if it is brown, but this darker color goes from the first quartile, first quartile, so it is the 25th percentile, to the third quartile, so the 75th percentile. And the difference between the values that correspond to the third and the first quartiles, this difference is referred to as the interquartile range. So it is very simple. But what it is very interesting is repairing that the interquartile range is a measure of the spread of the distribution. So it is the non-parametric counterpart to the standard deviation, which is quite interesting. So in our example, well, it is roughly like 0.6. So it is the variable, the population in 1930. This 1930 means the population in 1930. And this population for the Chilean cities has been previously transformed in logs. So this data is data in logs, okay? Log of the populations. And what about these horizontal lines that are drawn at the top and the bottom, top and bottom? Well, they are the so-called fences or hinges, and they correspond normally to the values of the first quantile less 1.5 by the interquartile range. So in our case, more or less 4.6, and if you go up, is the third quantile plus, so you add to the third quantile this part, and this part is the equivalent to 1.5 by the interquartile range. And why multiplying by 1.5? Well, it is more or less like the 2 by the standard deviation. So in order to identify the outliers, as you know, so the observations that fall outside the fences are considered to be outliers. So this is the non-parametric counterpart with what we do with the normal distribution. Instead of the mean plus 2 times the standard deviation, in this case, it is the median. So it is, you know, not exactly, but what would you do is from the third quartile and the fifth and the third quartile, you are adding 1.5 the interquartile range to establish the fences. And more or less, what you could suppose is that 95% of the data is going to be, as I said, more or less roughly inside the, you know, these fences. Okay. So the observations that fall outside. So in this case, we have only 2, well, perhaps 3, but more clearly 2 cities, because they are cities with population size clearly far from the rest of the Chilean urban system. This is what we are saying, which is very interesting to have this this view of the box plot. Well, as I said, in this example, we are representing the log population size of the Chilean cities, and we have these 3, well, more or less 2, no? These three values are the most important cities at that time. Well, I think that ever in Chile. Like Santiago, the capital city, Valparaiso, which is the main harbor, and you know, like the exit to the sea for Santiago, and Concepcion, which is at the southern part of, more or less to the south, not the southern, but more or less to the south. The typical multiplier for the IQR to determine outliers is this 1.5, but as you know, Geoda, and of course with any other software, you can also establish a value of 3.0. So 3, if you multiply, you know, the interquartile range by 3, and you sum up the first, or subtract the subtract in the first quartile, or sum up in the third, maybe you are not going to have outliers at all. So it is in order to detect the truly extreme observations when they are. So you have the outliers, but the truly extreme observations could be detected if you use this multiplier, the 3 instead of 1.5. You can see all these ideas where they are not mine. They have been more or less copied from Anselen. The Geoda workbook I was referring to the other day from Anselen. So Anselen is renewing his workbook almost, well, I don't know if every month, but maybe every 3-4 months, he uploads something new in the software. So with new versions of the software, and of course introducing the corresponding part in the workbook. So the workbook is highly updated, and you can find it here. So it is here in documentation. This is the Geoda workbook I'm referring to. So you can find everything in the last version. So all the items, all the functions that you can find in the last version of Geoda, they are fairly very good explained here. So it is not completely in depth, but quite in depth. So I recommend this workbook, even to learn about the theoretical part of it's not just a click here or click there. Of course, you have all these recommendations, but also you know, brief explanation with interesting references part in order to help you to learn. Okay, so let's go on. What about if I compare, you know, the evolution in the box plots? This is a very interesting analysis. This is a spatio-temporal, you know, so comparing the box plots over time, because you can identify trends. Trends in what? trends in the mean and trends in the dispersion of the cross-section distribution. So the mean part, as I said, is the part that is represented by these lines, these red lines that are the median, and the dots, the green dots, they are the mean value. And the dispersion, well, it's an equivalent to the standard deviation, could be the size of the box. The box size is more or less like the standard deviation in this non-parametric setup. So as you can see here, we have represented the log population size of the Chilean cities over the whole period we were studying in the paper. So from 1930 to 2002, okay? And first, we can observe very clear an upward trend. So from the first, moment of time, from 1930 to 2002, so Chilean cities have experienced growth in size. Of course, it is normal almost everywhere in the world. This is for the first moment. So the first moment is, I can see this first moment with the median and the mean value. But what about the second moment? Because for the second moment, what we can see is that the boxes, are more or less equally large. So I cannot see, a lot of variation in the size of the boxes. But as you know, this is a biased indicator for dispersion. Why? Because, it is related to the mean value. So if you have an increasing trend for the mean value, so this dispersion is also dependent on this mean value and dependent on the distributions. So what we should do is, computing some kind, because this is not exactly this concept, but a quasi variation coefficient, So the Pearson variation coefficient, as you know, what we do is correcting the standard deviation by the mean value. Here, what we are going to do, because it is quite easy, even visually, is correcting, the interquartile range by the median. Since the median increases, but the interquartile range remains more or less stable, what we can see is that the variation is going to do down, so it's going to decrease. We will have a decreasing trend in the dispersion measured as this quasi variation coefficient, this unbiased measure for dispersion, which is very important. And so we, and even if we take into account the upper outliers, we see that perhaps here we have almost three, here it's only two cities, and from 1970 only one very, very big city, very different in size from the others in terms of size, because it has been growing a lot. That is the capital city, Santiago. So as many people say in Latin America, they say that God lives everywhere, but he has his office in the capital city. So in Santiago, in Lima, and some other places, because they are highly centralized countries. So, and this is what is happening. So Santiago is also experiencing an increase in size, but the other cities have been caught up by the other. So the Valparaíso and Concepción were caught up by the other big cities in the country. This is what we can see here, So if we represent this Pearson's, quasi-Pearson's coefficient of variation, we'll have more or less this. This is, as you can see, we cannot build that in GeoDA, so this is Excel. If I represent these values in Excel, we find a decreasing trend. So this chart, this graph, with the Pearson's coefficient variation or the quasi-Pearson's if I use the median and the interquartile range, what I get is the so-called sigma convergence. Maybe some of you have heard about the sigma convergence, because when we talk about convergence in regions, for instance, one of the main and very simple measures for convergence is the sigma convergence, which is based simply in the evolution of dispersion. So if we have that dispersion, so this this variability in both sides of the mean value is experience a reduction in time, we could more or less say that we are going to a convergence. So we are convergence. Why we are converging? Well, in this case, the Chilean cities experienced the convergence in time. As I said, these big ones were caught up by the other ones, and with the exception of Santiago, that still continues very, very far from the rest of the distribution in terms of size, the other ones are closer to the mean values. This is the idea, which is a kind of evidence of convergence. But we must go further. So because this measure for convergence is a first measure, we should, if we can, of course, go in depth to this idea. This is why we go further and not only use these box plots charts, which are very common in this kind of analysis of convergence, trends, etc., or even this line graph. We should go further, as I said, because we should identify any other structures inside this convergence trend. Let's go to the scatter plots. Why using scatter plots? Because there is another concept for the convergence, not only the sigma convergence, sigma because deviation, but the beta convergence. Many of you perhaps have heard about this beta convergence. There's the beta convergence in the neoclassical growth models is the beta coefficient, in a regression, in linear regression, as the one that is depicted here, even a simple regression without only one explanatory variable. This explanatory variable is, the variable at the starting, at a starting point. So in our case, we had taken the log of population in the starting point of our analysis, 1930, and in the vertical axis, so the y variable, the dependent variable, is growth. So it's, you can calculate growth like, the growth rate from 1930 to 2002, or you can compute somehow an annual mean value for this growth rate if you divide it by 7, I think, that are the, the different periods here from 1930 to 2002. And this is what we did here. So it is a log of growth from the beginning to the end. And what we see is that we get here a slope, a negative slope. So this negative slope is a sign for convergence. Why? Well, the neoclassical theory thinks that the regions that starts more, with, for instance, less population or more poorer regions in terms of income, if I was measuring income, these regions are going to grow faster than the ones that have higher values at the beginning or the starting point in time. And this is why higher growth rates corresponds with lower initial values, and vice versa. And but this is for the whole period in our example from 1930 to 2002. But what about if we split this period of time, which for the Chilean history is, it's very diverse in terms of in economic terms, even for the evolution of the cities. Okay, if we split these scatter plots in two, so why in two? Because I could consider a first subperiod from 1930 to 1970 and a second subperiod from 1970 to 2002. Yeah. Again, if you know the history of Chile, you know that in the 1970s, Chile experienced a huge change in socio-economic terms. So Pinochet, the dictator, rise to power, and the political economy, the ISI, so this substitution industrial protectionist, policy applied to the national industry was substituted by a promotion of the services. And this changed the urban system in Chile, and changed a lot of social issues in this country. And this is why we suspect we could have a structural change in terms of, these subperiods of time. This is the idea. So we had this, you have here more or less what I was saying, and this change during the 70s. And what happens with convergence? Well, we have convergence in the two subperiods, yes, but the convergence speed was slower after 1970. So yes, we have convergence throughout the whole period from the 30s to the 21st century, but this speed of convergence wasn't the same, or wasn't as fast in the first subperiod than in the second. So in the second subperiod, this convergence among cities stopped. Why? Because Santiago is going to go up, to escape again. So the city sizes were converging to a central point until the 70s, and then in the 70s, well, convergence continued by in the lower part of the distribution, but not for the capital city. This is what we found. It is very interesting because we are now splitting in order to detect or to see if we could have a structural change also in the urban distribution of the Chilean cities. Because of course it was a structural change in political, in social terms, in economic terms for Chile, but we needed to see if particularly for the population size we had also this issue, so significant changes in terms of convergence, for instance. The Moran scatter plots are also interesting to analyze this. Well, in this case, we go to the global analysis again, and to see if we have for population a kind of convergence of divergence. So what we do is computing the Moran psi, the index, and depicting these dots are the city sizes, okay, in these four quadrants. If you remember, the four quadrants, what they do is standardizing the variable. So the main variable, the log of population, is standardized. And what we do is representing in this first quadrant high values of so cities with a log population over the average of the urban system that are surrounded by nearby cities that has also, in average are also higher or largest in terms of population. This is the high. The low in the other extreme, you have the lowest cities surrounded by, in average terms, cities that has also a lower size. And these 2 and 4th quadrants are the ones for the outliers or the negative spatial autocorrelation. Well, what it's it is very impressive is that we don't have a huge amount of spatial autocorrelation. In fact, this value is almost very close to 0. If we apply the permutations inference and get the pseudo p-value to see if this value, this low value, could be statistically significant for spatial autocorrelation, we see that, well, yes, it is significant at 99%, so we can reject the null that of absence of autocorrelation, or we can accept that we have a spatial autocorrelation in city sizes during the 30s. But this goes drastically down to a non-significant and even negative, okay, but non-significant. This value, this negative value, in fact, is 0, or must be taken as 0. So we don't have a spatial autocorrelation in the distribution in 1970, and we don't have even in 2002. So what does it mean? So it means that we had a kind of polarization, not a lot, in cities in the first in the starting time. So cities that were high, large, were more or less close to others that were large, and smaller cities were surrounded by smaller ones, but this disappears. So we don't have this polarization, we don't have this spatial autocorrelation, so it is more stationary because we go to convergence. So we go to a more homogeneous, distributions with no so polarization with extreme values or even different modes, etc. But if we depict the LISA maps, what happens? So if you remember, the LISA maps, what they do is taking into account significant points in these quadrants, because what we find in the Moran side is a global spatial autocorrelation. Sometimes the global spatial autocorrelation is not very significant, or is not significant at all, but you can find certain clusters that are local that could be statistically significant. So these, cities that could have in these quadrants a significant statistical value as a high point, or a low, or a high low, or low high. This is what the LISA scatterplot does. And so we only had, for the global autocorrelation, we only had a statistically significant value for the starting point, but not the others. If we analyze what happens to the LISA cluster maps, it is interesting. So in the 1930s, of course, you have this polarization. So large cities were more or less concentrated in the upper part of the country. So this part that connects with are close to Bolivia, and this is Arica in the limit with Peru, and some other big cities in maybe Antofagasta and some others in the minor area of the country. Here it's curious because it is the center of the country, and you have these low values that are, but also some other cities that are high but are surrounded by low. Here you will find Santiago. So joined to Santiago, you can find some cities, but they are not joined, but more or less separated. And in the middle, you have other cities, but much smaller size. This is what this is why this high low and low high are considered as a negative spatial autocorrelation because it is high surrounded by low or low surrounded by high. This is what happens in the city, in the center of the country. Also, something similar here with low cities surrounded by high, which is quite similar to this place. Concepcion could be here, and these cities in the very southern part of the country, well, are not very significant, with the exception of this part. But these two ones that are very close to the South Pole are not significant at all. This is what means these cities in gray color. And the evolution is clear. The evolution is to, in the 70s, absence to spatial autocorrelation, and a depicting trend again to a spatial autocorrelation in local terms, not in global terms, but in local terms. Again, some differences. In the northern part, again, bigger cities or larger cities. Santiago, is surrounded by others that are also largest. Not at all, of course, but we can see that this we had a convergence trend towards 1970s, but from the 70s, this convergence, reduced the speed, and even we could go to some kind of this divergence, not for the moment, but perhaps if we introduce data from the new censuses in Chile, we maybe could find this dispersion trend again. What about the average charts? So the average charts is an implementation. This is an output from Geoda. It's an implementation of this test, a t-test of the difference in means between selected and unselected observations. So what we do is selecting one part of the urban cities in Chile. What I don't know if you can see here, but in the map we will see now very quickly. This is the central part. So these are the cities that are part of the metropolitan area of Santiago. So these are the ones that have been selected. And what I do is analyzing the average, the average value. So the average size in the urban cities in logs again for the selected versus the unselected sample, or cities. So it is interesting because the selected metropolitan area was in size smaller. So because they are a few cities compared with the rest of the cities in the countries than the rest of the cities. In the 30s, you could find quite very big cities like Concepcion or like Valparaiso, some others that are not included in this sample. But the most important thing is that we could consider two Chiles, maybe. So the central part of the country, or also the metropolitan area part, versus the rest of the country. Why? Because the evolution of the mean values is not the same, as you could see. From the 70s, this changes a lot. So this is the same small sample, but in size, it has grown a lot. Maybe because Santiago has grown a lot, maybe because Santiago is red here, surrounded by some others that are also bigger. And this is why we can find here this change, in size, this inflection from the 70s. So the 70s could be considered as a clear structural change, and we don't know exactly for the moment, but it could consider the metropolitan area of Santiago as a spatial regime, which is the equivalent to the structural change in spatial analysis versus the rest of the country. Okay. Yoda also gives you because it is like a difference in difference analysis. It was said here. It is a difference in the means, so it is a kind of a difference in difference. This is here you can see run diff in diff test. This is the test for difference in differences, and so here. So for 1930, the log of population, if you split, so the metropolitan cities versus the rest of the country, this variable space gets the value 1 for the selected and 0 otherwise. And what Anselen do here, what he does here, is computing an F value. So it is the F that compares estimating the whole, like a HO test, something similar. So estimating for the whole sample, or estimating two different regressions for each of the samples, of the subsamples, and see if it worth estimating two regressions versus an only one. So because you have this parsimony principle in econometrics, so if you do something more complicated, it should be because it works. If not, go to the simpler one. And but this is equivalent to the t-test, the probability of the t-test, okay? This is what it does, and if we compare what happens in 1930 compared to 2003, in 2003, this role of the metropolitan cities that is represented by this variable increases. Well, it is significant too in 1930, but less significant, only for 91, 92%. Here it's clearly more significant, 97% over 95%, which is more or less mandatory in statistics. Okay, and so it is interesting because it is revealing, as we said, a different evolution. So this chart is really amazing, you know, because you see this inflection from the 70s for this metropolitan area cities, particularly for Santiago, as you could see before. So Santiago even grew more. So all the cities grew, of course, but they approximate each other. But Santiago even escaped more in terms of size. It is very interesting what I'm doing, because you should do the same with your own database. So, you know, it is completely unacceptable that you go into the model, you go into the regression model or whatever model without looking at the data, without knowing what is going on inside the data. This exploratory spatial data analysis, or spatio-temporal in this case, is completely crucial, because if not, you are like in a black box. You cannot afford to considering your data as a black box. If it is a data on your own research, for your dissertation or for whatever, for a project or whatever research, or if it is data for, you know, a company because you are doing some kind of consultancy studies, you cannot afford, you know, to treat the data as a black box. You must know, go in depth, trying to identify, even studying. I had to study Chilean history with Andres because I had only, you know, a brief idea of the first Spanish conquerors and this part of their history, but not the more modern one. It is important to study the phenomenon you are analyzing, also just to explain what the statistical part is giving to you. And the kernel functions, well, we saw some the previous days, but just to showing what is going on here. And the next day, I will show you how to compute them. But of course, it is quite simple in R. These variables are the relative log population. Why the relative? Because we wanted them to have the same mean. So the mean value is 1, and this 1 indicates the average city size in Chile. and 1.5 could be a value 50% higher, and etc. What we see, if we represent, well, the first and the last periods, it is, of course, almost mandatory, but it is interesting also to give, information of two intermediate parts. So why in the 1950s? Because it was the moment for the ISI protectionist policy, the moment more or less where this policy was implemented. So the 70s, because this policy was removed and changed by another policies that are more centered in the tertiary sector in detriment of the industrial one, and this is why Santiago is escaped so much, because of this centralized nature of this country. And what we can see is that compared with 1930, so this dark line, continuous dark line, more cities reported values below the average, the Chilean average. As you see, this is the shift towards the left. And also a shift here. So smaller cities tend to catch up the biggest ones, but to a value that is a mean value that is below the average. However, the biggest value, the largest one in the country, Santiago, remains at the same point, at the same distance with respect to the mean than in the previous years. So there's no convergence with this city, with this peculiar city, okay? This is what, so we are reaffirming what we saw before with the other charts. Well, in the end, we saw that for certain reasons, we shouldn't consider just the central cities versus the rest of the country. Why? Because we had the different parts of the rest of the country, since Chile is like a line from up to down. You have this part of the line that is in the northern area of Santiago, so the northern regions from Santiago to Peru, and the southern regions from Santiago to the pole, to the South Pole. Why? Because they were different. So the cities in the north are, if I could say, more Spanish, because they were founded by the Spanish conquerors, and they were very important, in the connection with the main city at this moment of time. That the main city was Lima, where the vice king was there, and these cities were very, very, very big. In fact, in the northern part of Chile, and not only because of the minery, but because of history. In the southern part of the country, it's different even in from the environmental point of view. So in the north you have like a desert, but in the south you have woods, and you have green spaces, and even ice in the very southern parts. And this was the part that the Spanish conquerors couldn't, conquer because of the Mapuches. And this, this configured a different kind of, even of urban settlements that weren't the same as the northern cities. This is why we tried to see if we could find differences, and we found them. So the evolution, if you look at the northern cities, well, the central ones are more or less similar to, with this shift to the left, and very similar in this shift here of the smaller enclaves. So it is very similar to the general trend. But if you compare the northern cities with the southern ones, they are not the same. So we decided to split. So to consider three Chiles, not the classical metropolitan area versus the rest. So there's no the rest. You have the northern part and the southern part of the country. Cities in the northern regime have a changing bimodal shape. So it's, in the beginning, you have these two modes, but in the end, these two modes are more pronounced. And in the southern cities, the convergence trend seems to be more acute. So cities in the southern part of the country converge to a club, because this is a separate part of the country, but they converges, and this convergence trend is not so clear in the north. So in the north, they are experiencing, as you could see with the LISA maps, here around Arica, in the southern part of Arica, a growth in this city size. Why? I don't know. Maybe because in Arica they have developed a recent intensive agricultural system, close to the one we have here in Almeria or in Israel. And maybe because of the Asapa Valley, and I don't know, the Chilean guys that are listening to me could say why, but these cities are experiencing, a growth, and this is why the evolution in the southern part of the country goes more clearly to convergence than the evolution in the north. So for these reasons, we decided, to split the country into three parts. And now I will show you briefly Geoda, because if you don't know Geoda, the ones that do not know very well this software, I will show you some functions that could be interesting. Well, Geoda needs a kind of blank sheet here, because if not, it is a mess. So if you open Geoda is just, a menu here, like floating, and all the charts and the maps are going to float again. So this is why I prefer to have a blank sheet at the bottom. And well, sometimes what you have is a database like the one I had here. Yes, it was like here, assignment 3, data for classes. Okay. So normally you have something like, some of you found an initial panel. So you open the initial panel. It's a database that is organized in such a way that you have a pool panel. So all the years, or so year by year, or even region by region, you have stacked, the cross sections or the time series, one below the other, and this is the situation. This is some of you asked me, what should I do here? Well, a very simple way to to prepare the database is using, sorry because it is in Spanish, but it is quite similar to the French version. So insertar is insert. You can insert a pivot table, tabla dinámica, pivot table in English. So if you select all the from A to Z, okay, and accept. What you should do is organizing, and in rows you should in rows, filas is rows, you should identify, or you should depict the region. So this is the region code, region code, and the time series could be in columns. And well, the population, that is my database, should be here. Well, in form of sum or averages, it doesn't matter, because I'm supposed to have only one value for each of them. So it is just, well, I could also arrange, if I ask, to organize these the rows, because it is interesting for Geoda that the code could be stored as an array or character. This is why they are, put to the left side of the cell in Excel. But if I ask to order, or maybe I can't. Let's see. So I should copy, maybe. maybe it is easier now to copy the pool data, to open a new sheet. So this is the regimes code, and I could order by this column, and it is going to ask me if I want to order this column that is an array as if it were a number, a numeric, and I say yes. So I have everything corrected, okay? And well, I recommend you, if you have this case, to put a prefix like a population or something, not the years, you know, because, but it is better, just in case. Okay. So what happens if you have prepared your database? This is the one that I have prepared for you. Why? Oh, I cannot open it. Oh, okay. Well, sometimes what I have is a database that is stored in Excel file or a CVS or whatever. If it is in Excel, please be careful, because, well, it is this kind of a stupid thing that can stuck you there, and it is just a way of, you know, of reading the instructions that sometimes they are not very interesting. You don't read the, you know, the manuals. So I will tell you. Well, here I have the population, the same as data as the other, but with the names of the cities. And this is the log of the population and all the computations here. And this is, you know, the log divided by the log of the for each year of all the urban system. Okay, these are the database I'm going to use. And just one stupid thing, as I said, but very, very important. Please, it is stored in XLSX. Well, Geoda cannot open these very modern Excel files. So you must store the Excel file, if you have an Excel file, okay, in the older version. So the older version is here, Nestoras data for classes, and something that is stupid, as I say, is very important if you want to open it in Geoda. So Excel 97 2003, okay? If you store it like that, you don't have problems. So this is your database. Your database, if it is separated from the map, because sometimes you have the map with the X and Y's from a different database, and you want to, you know, to join this the database for the map with the database that has been prepared here in Excel, you should have a common field, that is this field 1, that is in our case, because also the name could be this common field, but with the name it's a problem, because sometimes you know, the accents, these Spanish accents, as you can see here, you know, are not correctly stored, or even the our special letter, the ñ, you know. So it is quite complicated. So I recommend you always to have this field that is a numeric code. If you have a numeric code, please store it as a string, as a character, because it's the one that Geoda is going to recognize. If you have also, as you can see here, the formula, please delete the formulas. So it is very easy here to see, as I have computed in a different, I'm not going to delete the formulas, because I have stored it as an old XN, oh, sorry, what happens? Say copy and paste, and I passed as text. I don't know why it is so slow. So it must be installing something that I don't know. So well, if you have formulas, the best option is eliminating them. Oh, I don't know why. Let's see here in pastas values. Okay, so I store. Well, it says that it is an older version. I say yes, I know. And suppose that your map is stored. Your map could be stored as a map, or as again a CVS or whatever text file or a spreadsheet file with the coordinates. This is the case of this city base in which you can see the coordinates for the regions, and well, here you have the database again, but suppose that the database is not here, and I want I'm going to delete them to do the exercise. So the interesting thing here are the X and Y coordinates. This is what I need. And again, I should store this Excel file with the old version. So here, I don't have the map, but I could have a map if I have the coordinates, because Geoda can convert the coordinates into a map. Okay? This is a map. So these are the functional labor market areas in Chile, and this is a map. Why? Because a map in the ESRIS type of map, so the ESRIS type of map, the shape files are based on three or four files. So the DBF, the projections file, so the DBF is the database, the shape file, so the one with the coordinates, the drawings of in this case, it is a polygon map, and the one that connects shapes with DBF, okay, the SH. And well, since this is a map, you have the map prepared. But what happens when you have only the coordinates? So the coordinates could be enough. So they are not so complete, but they could be enough, as I said. So if you want to open an Excel file, you press here in Open File, and you come here and ask for Microsoft Excel, XLS only file. And you will find the city base and the population. So I will open the city base, because in the city base I will find the X and Y coordinates. This is what I have, the X and Y. So this is a table, but in this menu, in the tools menu, in shape, you can convert these X and Y coordinates into points from table. Geoda asks you for the X coordinate and the Y coordinate. You say OK, and it depicts the points, on the map. And these points, it's like a picture, but this is not a proper map. So to have a proper map, you must store it as a map, as a shapefile map, in order to create these three files that we saw, the basic ones that are the DBF, the shape, and the SHX, not the projections, if I don't have the projections information, as it is the case. But with these three ones, it could be enough. And as I come here to File, in Save As, I must store this view as an Esri shapefile. Esri shapefile, and it is going to ask you for, a name for the map. So the name could be Chile map. And that's okay. So I should close the view and you know, in the table. And to close everything, I can press here. They say that the geometry have no. Do you save them? No. I say no because I've stored the map. That is what I wanted to do. And now here in open, instead of pressing I want to open an Excel file, I will say open an S3 shapefile. Okay, and Chile map, open, and I have the map. And this is a map. How do I know that this is a correct map? Well, a way of knowing that is here asking for a base map. Well, the base map puts, you know, a map of the world behind your dots. So if I say I want a cartolite, I can see Argentina, Bolivia in the Chilean cities in its context. I can press here and look more brighter, or perhaps it is better than here, change the map transparency. Sometimes the map transparency, so it is not very transparent. So if I say that I want it more transparent, no, or even no base map, so you have here some options that allows you, you know, to change the first configuration. Okay, so you can see here these two dots are the southern cities in the country, and well, these are the cities that depicted as we saw, as I showed you in the slides. Okay, but now an interesting thing, if you want to compute, for instance, the Morantz scatterplot or the Lisa scatterplot, I need a spatial weights matrix. Okay, so this spatial weight matrix must be computed, but where? In tools. In tools, there's a way to manage the weights manager, you know, and you can create. In create, well, you need an ID variable. If you don't have the ID variable, you can create an ID variable. So it creates the poly ID or just the ID as you want. You can, you know, edit this variable, add it, and this is a variable that has been created to the table. And in this table, this variable goes from 1 to the last number corresponds to the sample size, you know, and it is a different ID for the different rows or the different regions or cities in this case. We opted to compute a distance weights matrix. So for the minimum distance at which you know, the cities have at least one neighbor, and we use the inverse distance weights. So it's a way that not only puts 1 for the neighbors and 0 for the non-neighbors, but this one is refined with the inverse of the distances among cities in this area, in this country. So if I create this weights matrix, I can call it d-inv. So inverse distance, or in Spanish we say distancia inversa. So this is why I call it d-inverse. You can say d or whatever. Okay, so it is the distance but inverse. Well, it says that since it has the projection, maybe it is not going to be correctly computed. I say yes, proceed, doesn't matter. And I can see how they have been computed. For instance, this is the connectivity visual chart for the distance matrix. So this is the distance, so in miles. So the number, you know, of neighbors from one city to their neighbors, and at 1 mile, 2 miles, 3 miles, etc. And if I, for instance, ask for the connectivity map, if I press here, I can see their neighbors, just to see if they make sense, okay? And the connectivity map is a way of showing the connection, so I can, you know, approximate to these very connected parts. So perhaps it's, you know, too strong, the connections, so I could change the spatial weight matrix and choose other kind of spatial weight matrix, like having only 3 neighbors or 4 neighbors or 5 neighbors, which is another way of computing spatial weight matrices. Okay, and so we have the spatial weight matrix. What about if I have downloaded a map and I want to eliminate the islands? This was one of the issues here. You can do that. Suppose that I don't want these cities in this northern part of the country because they are quite isolated, because they are not very well connected, and blah blah blah. Okay, I can select with the selection point here all these ones and store the selected here in file, save selected as, and save this as a different map without these dots. I can select the observations, but using the table selection tool. For instance, I could select the ones that belong to the metropolitan region. So the MR column gives the value 1 to the cities that are inside this metropolitan region and 0 to the others. So I say yes, okay, select all in range. You can see these ones that have been selected. I don't know if it is easily if they are depicted. Select all in range. Well, I can now see if I have done it correctly. Save selected as, and I can here save it as a map with the name instead of untitled. I can put here MR map. So it is the map with the metropolitan region cities, and save it. Okay, apparently it has done it, and I can superpose the new map on this one. How? Using this plus sign at a map layer. So the main map is this one that I have opened first, but I can superpose a new one. Even I can do different things, interconnecting the maps. So if I ask to open the metropolitan region map, open, they have been superposed. I cannot see them, but if I put them up, I could see these gray dots. Even I can make them bigger, change the point radius to, I don't know, 5, 6, whatever. Oh, no, it is not correct. So I didn't do the selection correctly, because, you know, I have all the samples selected. So how can I delete? How can I delete this? Well, I must look for this small, where it is. Oh, whoa, I cannot see. Selection tool, let's see. Well, I can't delete everything, or where is it? Oh, no, it is not here. Oh, sorry. I see that it is quite late. We can stop here. It's a pity. It's a pity because I couldn't find this exercise. So I can delete everything and start again. So I say they are unsaved data, yes, no, and open. Since they are stored here, open the Chile map and try, no, if I can, in table 2 with the selection tool, try to select the selection variable. Well, I hope it is correct. Select all in range. No, maybe because it is not correct. Let's see to the table. Yes, the metropolitan region gets 1 for Santiago and the city San Bernardo that are around. Yeah. So something is failing with me. I'm not doing this correctly. New selection. Maybe I should select 1 and 0. I'm not sure. Invert selection, no, because I don't know why. Maybe selecting only the ones that, yes. So I must set 1 here and 1 here because it is minor or equal. So it is 1 and 1 and only selects the cities that are in the metropolitan region. And now if I ask it to save selected as, I can save them. I can overwrite. So I can write MR map save. This warning allows me to replace. And now if I want to open this part here again, I can open the metropolitan regions, only 22 selected. I can the point radius, make them bigger, and okay, and establish. Well, there are some others, as you can see, base maps. I usually take the Carto one because it is gray and do not distort a lot with the dots. But of course, you can choose whatever you want. And the map transparency here, okay, close. So if I come to the metro area, I can see these dots correspond to the metropolitan cities. Okay, and that's it. So what else? I think that, well, for the next day, I will finish with Geoda and start with R. So first, I will give you more time for this assignment. So the most important thing for the assignment is that please look for your map. You need a map. Of course, you can work with a shape file from the very first moment. So I have here a shape file. I can open a third layer. If you remember, I had here and with the functional labor market areas. Oh, it says that it couldn't. So sometimes it happens with Geoda. So Geoda, it's not completely stable. But well, let's open this map and the one with the functional regions. Okay, so you have something weird here, maybe because of the. No, yeah, this is the problem with the projection. If you have problems with the projection, please ask me, because you need a projection file. This is why they are not one over the other. So if it would be correctly done, so in fact I have the projections file, but I eliminated. This is the problem when you take the coordinates without the projection map, that you must give projections. You can look for how to do that in the Geoda workbook. Don't be lazy, check the workbook, because here there are some GIS operations and gives you some clues to look for, you know, to give a projection to a database, okay? So it's a way of being familiar with Geoda. So for the next day, the ones that couldn't find your database, please, it is mandatory. You must have a database, a panel database, and you must have a map or a map made by yourself with the coordinates, or a map that you can find, you know, in a statistics office or wherever. Okay, If the coordinates do not match or are not correct, please take a look to Geoda, okay, and to select a projection, to reproject, etc., etc. Okay. I will give you some clues the next day. The next day, I will show you how to transform this Geoda map, that is a cross-sectional map, into, so you can close this if you don't like, remove, so and get this one. So this is a cross-sectional database. You can change this cross-section into a database. So Geoda allows you to do that with this menu, and you can compute these chart, average charts, and some other like the, as you remember, the box plot, but the box plot in a time series framework, as I showed you on the slides. Okay, but it is important that you have your own map and you can do your own exercises. The first thing, please have your database complete. Your database that should be stored like as in here, okay, like in the city base. Oh no, not here, but not in the initial panel, but as I build. Do you remember? Some of you have the database as in this spreadsheet, very long one, in the stacked form. Please change the stacked form for the form in a cross-sectional way. So in rows, you should have the regions, the cities, the countries, so the cross-sectional units, the spatial units, and in columns, you should have the time series. Normally, the number of cross-sectional data is going to be higher than the number of time series in this mentality that we have, okay? So I don't know why I cannot manage with this. It is weird. I don't know what happens. Well, sorry, because my computer is not very well today. So since it is quite late, please, I would ask you again to go to, today we haven't explained a lot theoretical things, but please, I would like you, to give me a feedback of session 3 in order to go. And of course, for the next day, also install the last version of RStudio and of course the last version of R. So I would like you to have installed, of course, Yoda, RStudio, and to have your database, okay? Because if not, we cannot go ahead. It is very important, at least for the DASEE master student, okay? So that's it.
Professor, but could you please check the data? You told that there are like 3 databases. Could you check it, please, and tell us, is it okay, so we can proceed with the analysis?
Yes, I'm going to check the assignment. Yes, I'm not going to give you punctuation to give a score, but I will give you a feedback as ever. So if you have something that is not correct, I will say, of course, don't worry. Or if something is missing, I will tell you, because it is very important that all of you have your database completely ready, in order not to get retired from the rest of your colleagues, and to reach to the last session as best as possible. Okay.
So 30 European countries in the European continent would be okay, because, for example, there is no data for my country, and I hope that does not interfere with the analysis.
Well, 30 units are not bad. The point is that if you want to compute spatial autocorrelation measures, you know that you need a minimum sample. So the minimum, very minimum one is like 30. So don't, it is okay. Just for this exercise, it's okay. For perhaps for a paper, you should try to, to get the regions, or to split the sample, if you don't want to have a small sample problems that with the, for instance, with the p-values, because the p-values are computed, even the ones for the Moran psi, supposing that you have a large sample. In this setting of big databases, so this is why you could have some problems if you have a small database, but doesn't matter for this exercise.
Okay, thank you very much, Professor.
So that's all. I'm going to stop recording.